Hey everyone, my name is Evan Casey, and I'm going to be giving a talk on Intro to Scala. Cool. So a little bit about me. I'm engineer in TAPAD, New York, startup, Hack and Y 2014 fellow. I work with Scala on a daily basis, doing everything from Hadoop stuff, distributed systems, to web programming and play, but we use Scala basically for everything throughout the stack at TAPAD. So if you want to follow along on this tutorial, you can fork or clone the repository at github.com/evancasey/intro to Scala. And so, yeah, let's go ahead. So here's a little overview. We're gonna talk about some of the basics of Scala, what it is, how it fits in with other programming languages you might know. Some basic principles of the language. It's a functional language that also has support for imperative programming. So there's stuff like type inference, higher level functions, and then we're also going to talk about some patterns, so closures, pattern matching, monads, and then finally, basically, why is Scala awesome, but why is it especially good for distributed systems? So before we dive into Scala, you might want to consider just like, two very common programming languages. This is Ruby and Java. So Ruby as a dynamic language, many people say it's concise, it's a scripting language, it has a REPL, the IRB, it has support for higher order functions, you can extend existing classes, duck typing, method missing stuff. And then, on the other side of the spectrum, there's Java. So, a very classic language, better IDE support. People say that they write fewer tests with Java code. A lot of open source libraries, good performance, JVM tools, better multi-threading support than Ruby or Python or any of the more modern dynamic languages. So that Scala basically stands for scalable language. And the reason that it was named Scala, scalable language, is that it's really designed for high performance systems, and it fills in a lot of the gaps in between Ruby and Java that sort of the feature set that both of them would like to have but couldn't until now. So Scala is statically typed, meaning that when you initialize a variable, that the type of that variable is not going to change throughout the execution of the program. It runs on the JVM and has full interop with Java, so this is super cool. Basically, Scala compiles down to JVM bytecode, so you can intersplice your Scala program with Java libraries or even full-on Java classes, and it'll all compile down to the same bytecode. But what's interesting is Scala has support for object-oriented programming. So it's not a fully functional language like Haskell or standard ML or something like that. You can actually create classes that have state, but you're not limited to only types. And this produces a style of programming that's very unique to Scala, or perhaps OCaml would be another example of a language that combines functional and imperative programming styles or object-oriented styles. But it is a functional language. It has support for all of your favorite things like higher order functions, composable types, things like that. But it has all the dynamic features of many of the dynamic features of Ruby and Python, and you can do scripting with it, all that kind of stuff. And it's got a really good way of doing concurrency with the actors model. So Scala is really practical because you can mix it in with your Scala and Java projects, use existing Java libraries, tools, Ant, Maven, JUnit, etc. Pretty good IDE support, so IntelliJ is awesome and has a pretty good library for plugin for Scala support. And you've got Scala specific tools like SBT, which is the Scala build tool. So we're going to dive into just a few examples now. So a basic principle of programming in Scala is the idea of type inference. So for example, I'm going to switch over to the command line now. And let's open up the Scala REPL just to show you guys how you can use that. So say I want to initialize an integer. So I'll call it x, and I give it the value 1, and I hit enter, which executes in the REPL. And you can see that, let me zoom this in a little bit more. The Scala REPL has actually inferred the type of our variable x to be an integer. And that's because the compiler notices that we've assigned the variable x a value of 1, which is of type integer. So this is a simple example, but it can also work for other things. So say we had a little bit more complex of a data structure. So we had some, a hash table or map, and we would like to map from ABC, which is the key, to a list of integer, 1, 2, 3. So when I execute this code, again, the Scala compiler is going to infer that this is a map of string to list of integer. So you can imagine that if you have more and more complex types, this becomes a more powerful tool. But you can also declare explicit types in Scala. So here's an example where we've actually defining the variable sum to be of type integer. And you might say, well, why would you want to do this? Because you already have type inference. But the idea here is that if you've got more and more complex types and classes, it's going to help a lot for your code readability to be able to declare these types explicitly. But Scala also has awesome higher level function support. So if you're say doing something like iterating over a string and seeing if it contains any uppercase characters, a Java example of this might involve initializing a Boolean variable to maintain the has uppercase state, and then iterating over each character in that string to check if each character is uppercase. And when the if case succeeds, the uppercase statement is updated, and maybe we would return that has uppercase variable. So this is a classic imperative example of how to do that. So you can write Scala code like this as well, but you can also use higher level functions, which enable you to do this quite a bit more easily. So here's the Scala equivalent of this, which is much shorter, as you can see, and the variable has uppercase is instantiated by just iterating over the name string using the exist function, which iterates over each iterable in the string class, for example, and checks is uppercase on each character. The same would work for lists or anything that's iterable. So this is great, and we can also do a lot of other stuff. So, you know, you could map over it basically all of your higher level functions that you may recognize from other language: fold, reduce, contains, flat map, all that stuff you can do in Scala. And there's more in the examples repository if you want to play around with that. But another great thing about Scala is that it was really designed to eliminate a lot of the things that people complain about in Java. And is that the syntax is very verbose. And if you want to initialize a class, for example, you know, in this example, we've got a class person that has fields name and age. You're going to have to write all this boilerplate code. So a constructor that allows you to set the initial values of name and age. You've got a getter functions for name and age, and then setter functions for name and age as well. So your class definition becomes, you know, all of a sudden a significant amount of code. But in Scala, you can do this in a much more concise fashion. So here's the equivalent of this in Scala. It's actually just one line of code. So we initialize a case class, which gives us the constructor for free, and also allows us to do class equivalence functions. So the case class is something that abstracts away a lot of things, but the main idea is that it adds some functionality to a normal class. And so with this, we have the you know, the building blocks of a class with getters and setters defined. So I'm going to switch over to the REPL now just to give you an example. So we would initialize a case class of person. We've got a integer, or actually the name, which is of type string, and the age, which is of type int. And we're going to initialize that. And so now the class is initialized, or the class type is initialized, and if we want to create an object of this class, maybe we'd say val p equals person of Bob with age 42. So as you can see, it's calling the built-in constructor of our case class, and now we can say maybe update age, so p age equals 12. Oops. Set it to val. P. Let's see here. P dot age is, so here's the getter, and the setter would say, I think this is a problem with the REPL, but let's say we want to create a new one, so we'd say val x equals, you know, person of Timmy and 22. Yeah, so you get the idea. Going on, so we're going to talk about a few more advanced features of Scala. One of these being monads. So there are a lot of examples of monads in Scala, and I'm just going to talk about a few. And the examples of monads that I'm talking about here are option and either. So you might have encountered these in other functional programming languages, but the idea of an option and an either, the embodiment of that like philosophy is that you can check errors through types, which means that you never have to check if something is null if you're using the option monad, or check if an error is thrown if you're using the either monad. The type has support for basically two options. In the option case, it's none, meaning that the variable was null essentially, but it then becomes a type of none, or a sum if there actually was a value assigned to that variable. So an example of this, might be, say you're parsing some JSON, you've got some fields that may or may not be there, and if a field is optional, you would want to assign that to a variable type option. That way, if the field is passed in, it becomes a sum, and if it's not there, it becomes a none. And then all of your higher level order functions are defined for these monads. So you could map over a sum, and basically the map would only execute the code in your map block if the value was defined. And a none would mean that the map block would never be executed. And the same with either. So say you're parsing some JSON again, and you've got a required field that needs to be there. So you parse it, and it throws an error. In Java or another imperative language, you'd throw an error, and then you'd have a try and a catch statement. But in Scala, the philosophy is that you want that error to be embodied in the type. So you can you would instantiate that object to a type of either, and if the required field was not there, you'd throw some error wrapped in a left that would be, field X is not available. But if everything worked out and all your required fields were there, then you would initialize it to a right. So again, one example of this is, say we had an option of type called O, and it's a type of option of string, and we've we set it to sum of hello. Whoops, that was a mistake. Okay, so here's O, and then say we had something that was an option of string as well, but there was, there's an error, so we call it a none. So now all of our higher level functions are available, so we could say o.map, let's say hello plus goodbye. Live coding, always fun. String, so let's give it a two upper, that'll work. Yep. Maybe two uppercase. Okay, let's say, give it a print line. So for each print line, hello. Okay, well, I'm striking out here, but let's do another example. So if we had a type of int, of some one, and then we map over that in the same fashion, and we say our wildcard is the variable we're iterating over, and then we'd say +1. So now we've got a sum 2. But if we have a case of none, for example, if our option of int is not there, and then we do a map over it in the same fashion, it's still going to return a none. So you can see how that enables you to treat the none or the sum option in the same way. Cool. Lastly, another really nice thing about Scala is pattern matching. So you can use pattern matching to unpack types or use them for if statements. So in this example, we've got a function what that accepts a type of any, and the type of any could be a int, string, or any other type because any is the most generic type. And we want to use this like a switch statement to print or return a different string depending on what the type is. So if we have a what, or if the what definition accepts a int, then the case of int will be called and it's going to return it's an int. However, if the type is a string, then it's going to return a string that says it's a string. But you can also use this for other types. So going back to our REPL, say we had our option of int, right, from before, so res5 is a sum of 2. So if we matched our option against a case of sum b, and let's say we want to return an int, so we're actually unpacking the integer out of the option. And then we'd also handle the none case, so we'd say none is returns a type of 1. And now we execute that code, and as you can see now, the match statement has returned a integer of 2. So what happened was our sum was matched against a type of sum, and since that match succeeded, it just returned the b, which is the integer nested inside the option. Cool. So that is an example of how to use pattern matching. That's all I have for examples today. There are a lot more examples in the GitHub repository. But finally, I'm just going to talk about like some really awesome tools that can be used in Scala. So at Tapad, we use Apache Kafka, Scalding, and Spark for a lot of our distributed, basically Kafka for our messaging queues and Scalding and Spark for our Hadoop jobs and data pipelines. These 3 open source libraries are all written in Scala and are really, really good for these types of problems. So if you're interested, I would highly recommend checking out these 3 libraries because they're awesome. Yep, and that's all. So you can tweet at me at ev_AndCasey, and also let me know if you're interested in working for Tapad. Thanks.